Hello everyone, welcome to SPEC eLearn, the online learning channel dedicated to chemical engineers. This video is part of the two-part series on optimization of distillation process. It will walk you through the part 2 of the series, optimization by heat integrated technologies. Heat integrated technologies. Most of the energy optimization approaches in the past concentrated on optimal reflux, feed location, and column pressure. The video on part 1 of the course deliberated on these approaches. Subsequent developments focused on application of heat integration schemes. The driving factor for the research and innovation for development of heat integrated schemes is the low thermodynamic efficiency of the distillation system. Thermodynamic efficiency. Thermodynamic efficiency of a distillation process is very low. Why is that? I will take few minutes in explaining this before we proceed to the discussion on various heat integrated technologies. The distillation column uses heat as the separating agent. In a conventional distillation column, high temperature heat is added to the reboiler and removed from the overhead condenser at low temperature. This external addition and removal of heat causes the overall thermodynamic efficiency of distillation to be low. There is a temperature difference between the heating media used in the reboiler and condenser. This figure is an illustration of a typical conventional distillation column where the reboiler is driven by steam and cooling water is used as the utility for the condenser. The heat is added in the reboiler at a higher temperature for generation of vapor reflux, that is boil up. The heat is removed in the condenser at a lower temperature for generating a liquid reflux. Hence, the separation of components is always accompanied by a degradation of energy even when the heat loss are neglected. So, what is the minimum work for separation? For a separation process, the minimum amount of work required to make a complete separation is given by the relationship that is a function of feed rate, changes in entropy, and changes in entropy. The equation shown here is an expression of this relationship. The maximum thermodynamic efficiency Emax is defined as minimum work for separation W minimum divided by the minimum energy required for the separation process, that is Q minimum. For an ideal mixture of n components, the minimum work for separation can be expressed as a function of the feed rate, the feed temperature, and the mole fraction of the components in the feed. The equation shown here is an expression of this relationship. The units of the various terms in the above equation are explained here. Actual processes operate with finite driving forces that are irreversible and therefore use more energy than the thermodynamic minimum. For a conventional distillation column, the minimum energy required to separate an ideal binary mixture completely when the feed is at its bubble point can be determined using the expression developed by Keller and Humphrey. This expression is a function of the feed rate, heat of vaporization, mole fraction of the component in the feed, and the relative volatility. The equation given here is an expression of this relationship. The units of the various terms used in the above expression are explained here. Thus, for a conventional distillation of an ideal system, the maximum thermodynamic efficiency, which is the ratio of minimum work for separation divided by the minimum energy required for the separation, can now be determined by substituting the expressions for minimum work and minimum energy. The maximum thermodynamic efficiency for a conventional distillation column appears to be very low, typically below 10%. The relative volatility, alpha, is the most important factor. A relative volatility close to unity leads to a very high reflux requirement. Consequently, to a high energy requirement in a conventional distillation column. The systems with the low relative volatility has the advantage for optimization. The systems with low relative volatility are therefore the best candidates for energy saving in distillation. Having explained the thermodynamic efficiency in little detail, we will now move on to the main discussion, heat integration technologies for distillation. This introduction is essential because this will help you while we walk you through the case study later in this course. Under the innovative technologies for heat integration, the most promising technologies are heat pump and heat integrated columns. Our focus will be on heat pump, which have been implemented in several industrial installations successfully with huge energy saving and economic benefits. we will touch upon the heat integrated columns as they are the emerging technologies with prospects, yet have several challenges in implementation. The heat pump technologies include vapor compression and mechanical or thermal vapor recompression. Heat pump systems are used to upgrade the low quality energy in the condenser to drive the reboiler of the column. In a conventional distillation column, the temperature of the vapor in the condenser is less than the temperature of the liquid in the reboiler. That is, Tc is less than Trb. Hence, the energy of the vapor in the condenser is at a lower temperature Tc compared to reboiler liquid temperature Trb. Hence, the condenser vapor energy cannot be used as a heat source for reboiler, the heat sink. It has to be upgraded to be useful. That is exactly what the heat pump system does. Vapor compression, thermal and mechanical vapor recompression upgrade the heat by compressing the vapor or a working fluid. The driving force that determines the heat transfer and the size of the reboiler in a heat pump is the temperature difference between the heat upgraded compressed vapor temperature and the reboiler liquid temperature TRB. At this point, we will introduce the term temperature lift. The temperature driving force that we have just discussed is a function of temperature lift. Hence, delta T lift is used as a guideline in the design of heat pump system. How do we determine the delta T lift? Come on, let's move on to find out. The selection criteria for heat pump technologies include the number of components to be separated, the product flow rates and purity specifications, the boiling point differences of the components. The selection criteria for the heat pump technologies also include the quantum of heat upgrade from the source, the reboiler duty and its temperature level. First, let us define the condensing temperature. That is, the condensing temperature of the heat upgraded vapor or simply the heat pump vapor. Denoting this term as Tc, Tc is usually taken as Trb plus 20 degrees centigrade. This will provide for reasonable temperature driving force in the reboiler. Once we know the Tc, we can determine the delta T lift using the expression given here. In this expression, T source is the temperature of the distillation column overhead vapor. On substituting and rearranging, we get delta T lift equal to delta Tb plus 20 degrees centigrade. What does delta Tb stand for? Delta Tb equals the difference in boiling points of the light key and heavy key components. The temperature lift is approximately 20 degrees greater than the boiling point difference. The delta Tb is an important parameter in the design of heat pump system. The technology selected depends to a large extent on delta Tb. Lower the delta Tb, lower will be the delta T lift and lower will be the pressure ratio of the compressor. How does the lower delta Tb and hence delta T lift and compressor ratio affect the heat pump efficiency? At lower delta Tb, the power required for the compressor is lower. Hence, the heat pump efficiency will be higher. Capital and operating expenses are lower. The efficiency of the heat pump scheme is measured by the parameters that include total annual cost and total operating cost. The optimum delta T lift is determined by estimating the total annual cost and total operating cost through a sensitivity analysis for a given separation at different values of delta T lift. Now let us move on to discuss the various heat pump technologies that are used commercially in the industry. First in the list is the vapor compression heat pump. The figure 1 illustrates the VC system. In this system, a working fluid is used in a closed loop between the reboiler and the condenser. This is the vapor compression heat pump system. The working fluid in the vapor compression system is a refrigerant which works in a closed loop. In this figure shown, focus your attention on the refrigerant loop only, which is depicted in blue and green color thick lines. Blue color is a flow path of liquid refrigerant. and green color represents the vapor refrigerant flow path. The condenser needs a lower temperature refrigerant which vaporizes, taking the heat from the condensing overheated vapor. The vaporized refrigerant is compressed to a pressure just enough to condense the refrigerant. Vapor in the reboiler gives away the heat energy for boiling up the reboiling liquid, thereby condensing into liquid. The condensed refrigerant liquid flows to the buffer tank to start the cycle again. The refrigerant selection criteria include large vapor density at compressor inlet, large latent heat. This will ensure the size of the compressor will be smaller and the capital cost will be lower. The application of vapor compression scheme is limited by the working fluid and the efficiency is low. When the components to be separated are corrosive, the use of mechanical equipment like compressors will be affected by corrosion by contact with the process fluids. Hence, VC scheme is not recommended for such corrosive applications. Examples of VC technology in industrial application include benzene-toluene separation as well as propylene-propane separation. Now we will move on to another heat pump technology, mechanical vapor recompression heat pump. This is an advanced technology and is widely used in the industries in the recent times. When combined with the vapor compression heat pump, this scheme eliminates the condenser. The Mvr technology is illustrated in this figure. Block arrows with brown dots represent the vapor line. Solid, light brown thick lines represent the liquid line. The overhead vapor from the column is compressed in a mechanical compressor. Compressed vapor is condensed in the column reboiler. The condensing vapor provides the boil up for the column. Part of the condensed liquid is refluxed to the column under flow control through a flash tank. The flash vapor joins the overhead vapor and goes to the compressor and the next cycle starts. Balanced quantity of the liquid from the reboiler condensate drum is drawn as a product under level control. The efficiency of the scheme is only slightly higher than the VC scheme. The Mvr technology is widely used in the propane-propylene splitter columns and butane-isobutane separation columns. Due to better performance, Mvr heat pumps are able to achieve better economic results over their planned operational lifetime, but they have a longer payback period. Now we will look at another heat pump technology, thermal vapor recompression heat pump. This scheme also eliminates the overhead condenser like Mvr, but with one difference. A thermal compressor or a steam jet ejector replaces the compressor. TVR has no moving parts, requires no electrical or mechanical energy to be driven, thereby making use of the lower prices for heat or fuel. Due to these reasons, the capital expenditure and maintenance cost are low. The MVR scheme is illustrated in this figure. The motive steam is used for compressing the vapor to a higher pressure so that it can be condensed by the vaporizing reboiler liquid. The major drawback of the scheme is a low reboiler load and compatibility of the process liquid with steam or water. The MVR scheme finds application where the heat load is low and in aqueous system, typically less than 2 megawatt reboiler load. Applications include peroxide distillation, etc. The MVR and TVR schemes are very effective because it attacks the problem of introduction and removal of heat from the column at the source. The pressure and temperature of the overhead vapor is upgraded by means of a compressor to such a level that it can be used as a heat source for the reboiler. By that way, vapor recompression is very useful technique for saving energy. The demerits of vapor recompressions are it is capital intensive and appear to be useful only for close boiling mixers. Close boiling mixtures means small temperature difference between top and bottom and hence small compression ratios. Close boiling mixture feeds are characterized by low relative volatility and small compressor duties are required for separation by heat pump system. Indeed, the potential for energy saving is the largest in the separation of a low relative volatility mixer. This fact is owing to high reflux ratios and as a consequence, large reboiler duties are required to separate these mixtures in conventional distillation columns. This table shows the comparison of heat pump technologies. VC heat pump and MVR heat pumps are widely used and accepted in petrochemical plants. MVR pumps have slightly higher efficiency than VC pumps. TVR is used for applications where heat duties are low and the process system is compatible with water, in other words, for aqueous system separation. Now we will move over to other emerging technologies which has potential for optimization of energy and cost in the future. Vapor recompression is a way to improve the energy efficiency of a single distillation column and is industrially applied for separation of close boiling mixtures. Heat integration technologies for a trade of distillation columns where commercialization is currently in progress include heat integrated distillation column and divided wall columns. These optimization technologies are still under development and not fit to be called mature technologies. In a HIDIC column, the stripping section is physically separated from the rectification section. Heat is transferred inside the distillation column from the hotter rectifying section to the colder stripping section. The heat exchange leads to gradual evaporation along the length of the stripping section and a gradual condensation along the length of the rectifying section. To realize the temperature driving force between the rectification and stripping sections, the rectification section is operated at a higher pressure than the stripping section. How do we achieve higher pressure in the rectifying section? A compressor is used to recompress and increase the pressure of the vapor leaving the top of the stripping section. This sketch is an illustration of HIDIC column. The feed enters the top of the stripping section. The vapor leaving the stripping section is compressed and sent to the bottom of the rectification section. The rectification section operates at a higher pressure compared to the stripping section. The rectification and stripping sections are thermally integrated for heat exchange, as shown in this figure. The high pressure vapor, upon entering the rectification section, condenses, providing the heat duty required for evaporation in the stripping section. This sketch illustrates how the rectifying and stripping sections are thermally integrated to provide the heat duty required for the stripping section. What we understand from this sketch you have just seen is that the vapor load in the rectification section decreases steadily downward in the section, while the vapor load increases steadily upward in the stripping section. The theoretical advantage of HIDIC column over a vapor recompression column is that in HIDIC the compressor operates only over the stripping section of the column. Therefore, a HIDIC should operate at a lower compression ratio and consequently a lower compression duty than a vapor recompression column. Lower compressor ratio and hence lower delta T lift is the main advantage of HIDIC. Due to this reason, HIDIC can operate at significantly lower delta T lift. Some recent studies have indicated delta T lift of 6.5 degrees centigrade is achievable for propylene-propane separation system compared to the Mvr heat pump. Theoretically speaking, HIDIC can operate without reboiler and condenser. But as a system, HID is provided with a reboiler and condenser as a backup so that when need arises, they can be used. Like Mvr heat pump system, HIDC is attractive for the separation of close boiling mixtures in moderate to high pressure applications. Studies have indicated that HIDC design reduces the energy need by 50% compared to conventional heat pump technologies like Mvr. For column for separating a feed consisting of 3 or more components, the configuration is fully thermally coupled distillation system. Fully thermally coupled distillation system is called dividing wall column DWC. Here you can see the difference between the conventional column and dividing wall column. In the case of a conventional column, for a 3-product system, distillation process requires 2 reboilers and 2 condensers. In the case of dividing wall column, for a 3-product system, the distillation system requires only 1 reboiler. This figure is an illustration of the difference between conventional distillation process and DWC technology. The DWC requires a single shell with a partition or a dividing wall that operates at one pressure. TWC is characterized by high pressure drop and high temperature differential from top to bottom. The feed side of the 2 compartment acts as free fractionator and the product side as the main column. DWC ensures that there is no physical contact between the feed stream and the fluid flowing on the right side of the wall, that is the main column. This makes it possible to produce a side stream product of required purity. This figure helps you to understand the working of the DWC. The feed consisting of 3 components A, B and C is pre-fractionated into 2 streams, the top and bottom in the pre-fractionator. The top stream contains A and part of B. The bottom stream contains C and remaining part of B. The term alpha denotes the split of B between the top stream and the bottom stream of the pre-fractionator. Component A is drawn as a pure product at the top as distillate. Component C is withdrawn as the bottom product. Component B is withdrawn as a product as a side stream product. This figure illustrates how the liquid split and the vapor split is taking place in the column. This is an important aspect of the design. The liquid and vapor are distributed between the prefractionator and the main column. The technological challenge is to get the control scheme for the vapor split across the prefractionator and the main column. With three components, DWC can achieve sharp split with pure components. DWC can handle more than three components also. In that case, lighter components may be present in the light key products. TWC requires the minimum vapor flow rate possible for any given separation compared to conventional system. The minimum vapor flow results in low heat duties and sizes of reboiler and condenser. The minimized vapor throughput and elimination of repeated evaporation and condensation results in reduced capital expenses and operating expenses. The residence time is shortened and the yield is higher. DWC has been used in several industrial applications on commercial scale successfully. Packed DWC columns constitute the majority of the application in the industry so far. Compared to conventional distillation system, savings that can be realized include investment cost less by 25%, operating cost less by 35%. DWC technology has been used by BASF Germany and Kellogg BP Amoco in commercial installations. DWC technology is slowly gaining popularity over the last 2 decades in the distillation world. For capacity expansion of existing distillation columns, DWC can be considered as an alternative technological solution. The debottlenecking of columns can be achieved with saving in capital cost and operating cost as well as higher product purity. Despite the favorable economics, the major drag on its wide acceptability in the industry is its complexity in design and control. In the next video, I will share with you a case study on Mvr heat pump. This is a real-world example of propane and propylene splitter in a petrochemical plant, so don't miss it. With this, we have come to the end of the presentation of part 2 of the 2-part series on optimization of distillation process. Hope this presentation with narration and animation was useful. Share with your friends and colleagues to reach out to large number of career-oriented professionals and students who are desirous of developing job-oriented skills and enhancing the knowledge base. Subscribe to our channel and get updates on the upcoming courses by pressing the subscribe button. It will motivate us to produce free, knowledge-rich video content for you. Thank you for watching.